So I'm going to go over example 4 from our notes for section 15.7. This is an example in which you're being asked to convert a rectangular triple integral into cylindrical coordinates. It is going to be similar to how we think about changing the order of a triple integral, in the sense that we're going to need to be able to redraw what our region is that we're integrating over. The thing is, though, is that this particular order of integration has z first, and we know that in cylindrical, z is also first. So because z is also first in cylindrical, we're actually going to be able to get away without having to draw our full 3D solid in this particular situation. If we had a different variable of integration first, we would have to go through and redraw the whole thing, because our surface to surface calculation would have to be transformed into a z first perspective. So we're still going to start the same the way that we would if I had to convert and redraw this whole solid, and we always start by taking your outer double integral and drawing the shadow. So I'm going to draw the xy shadow. And in order to do that, I need to make sense of what my bounds are telling me. X corresponds to that to the inner double integral. And so that's telling me that x is capturing my function to function movement. So x is going to vary from its bottom bound of 0 to x equals the square root of 1 minus y squared. And I know that when I draw this, this is going to correspond to my left function in my shadow and my right function in the shadow. My y values are told to range between y equals -1 and y equals 1, just using the bounds on my outer integral. And what I'm going to do to draw this region is I'm first going to just add to my drawing the restriction here on my y values. That'll help me make sure that I am focused on the correct region. If I were to draw my curves for my x equations first, I might see more of it than I need to. It depends on whether or not my window of y values is cutting things down. So I'm going to go ahead and draw guidelines at y equals -1 right here. And at y equals +1 right here. That's just to make sure that whatever I draw for my region sits in this horizontal window. Next, I'm going to go ahead and put my left function on the map. My left function is x equals 0. I know that that has to be the left boundary of my region. And my right function, the way it's written right now might be a little bit confusing in terms of figuring out what it looks like. I'm going to go ahead and square both sides, and if I square both sides and then take the y squared over to the left, this converts, and this is really just x squared plus y squared equals 1, but the fact that it is a positive square root tells me that it is the right half of this circle. So I'm going to go ahead, I'm going to draw the full circle, but I'm going to get rid of, I'm only going to work with the right half, so I can go back in and just erase this piece and this piece. There, now it's gone. So I now want to make sure that I shade the correct region. I want to make sure I'm only shading things between y values of -1 and 1. I know my left function, I was told, is this guy over here on the left. And so I am going to have a region that is bounded on the left side by the y-axis, x equals 0, and on the right side by that semicircle. So now I know what my region of integration looks like. So this is my shadow. once I have done that, I know that if this was a regular, if my order of integration was not z first, I would have to go into my z bounds and use those to draw my surfaces, my bottom surface and my top surface. So according to using those bounds, z is equal to the square root of x squared plus y squared, and this is a bottom surface, to my top surface, which is z equals 1. Now, as I said earlier, I do not need to draw this picture in 3D. The reason why is because I am not going to be changing my surface to surface movement in the z direction. That's still going to happen with z first in cylindrical. I'm still moving from bottom surface to top surface. But the one thing I do need to change is that my bottom surface's equation needs to be represented in cylindrical, and same with my top surface. So to write down what I just said, we don't need to draw our 3D object, but that's specific to this order. If x or y had been the first variable of integration, I would have to change it because x and y do not live in cylindrical, and the way I'd be moving through my surface would be different. So the reason why is because z is also a cylindrical coordinate. And will remain the first variable of integration when we convert. In cylindrical. We just need to convert the equations of the bottom and top z surfaces to cylindrical. So if I have z equals the square root of x squared plus y squared, that is really just z equals r. And z equals 1 is just going to still be itself, z equals 1. I don't have to draw the 3D object in this case, so I'm not going to bother doing that. I already have the shadow in the xy plane that I would need to generate from that solid so that I could set up an outer polar integral. So if I want to convert this integral, it's going to go from my outer double integral will be set up in polar. My innermost triple integral is going to come from converting. I'm still using the same bottom surface. My same bottom surface is that square root x squared plus y squared, but we said that that is really represented as r when we convert its equation. So z equals square root x squared plus y squared is really z equals r in cylindrical. That's still my same bottom bound because I'm still moving from bottom surface to top surface in the z direction within cylindrical, and the top surface stays as 1. Now the only thing that I am doing here that's going to be different is I'm going to set up a polar double integral to integrate my shadow. So I want to think about, if I draw sample rays, where do they enter my region and where do they exit? They are going to enter my region when r is 0 because the origin is part of my region, and they exit along a circle of radius 1. So, and the equation of that circle is r equals 1. So remember, this really is a function that I'm representing as my upper bound of r. It's just that it's a constant function. And then my bounds are going to be what theta values do I range between as I rotate counterclockwise through my region. So my leftmost, my clockwise most angle is down here, and then I am going to rotate through my region. So I'm going to go from negative pi over 2 to pi over 2, just rotating from the fourth quadrant up into the first quadrant. And then what goes in my integrand comes from my original function. My original function was e to the x squared plus y squared, so I'm going to need to convert that into polar or cylindrical. I'm not allowed to have x's and y's in cylindrical, so that's going to become e to the r squared. And when I convert dz, dx, dy into dv, in cylindrical, that will become r dz dr d theta. And so that means I need to make sure, don't forget the r that comes up when I convert dv. So I have a different integrating factor in cylindrical because I am integrating a different type of 3D piece. It's not rectangular, it's polar rectangular. And this is the final setup of my converted integral.